Okay, so the next speaker is Flavio Tonioni, which will tell us about the late-time accelerating cosmologies. So you can start when you want.
Okay, hi everyone. Thanks for being here. Thanks to the organizer for giving me the opportunity to speak here. So I will talk about late-time accelerating cosmologies, which is a work which is based on a collaboration I've done with Gary Shiu and Tran here at UW-Madison. So what I will say is based on a paper that appeared on arXiv in March, and also on an upcoming work that hopefully will appear in May. So before diving into the details, we'll spend a couple of minutes to explain the context in which our work originated. So we know that observations tell us that we are living in a phase of accelerated expansion, accelerated cosmic expansion. And on the other hand, there are a couple of general string-theoretic considerations that we can make. So the first one is the Dine-Seiberg problem. It's hard to find weakly coupled vacuum string theory. And basically this is because the couplings are dynamical. They are dictated by fields and by scalar fields, and therefore it's hard to balance different orders against each other to give a vacuum. On the other hand, we know that there are small coupling constants in nature, and a possible explanation to this could be that we are at the field space boundary. So the main idea that motivated us was to characterize the scalar field cosmological solutions that asymptotically approach the moduli space boundary. This, on the one hand, is a quintessence-like scenario for accelerated expansion, and it's also possibly an alternative to the conjectured absence of de Sitter vacua in UV-complete quantum gravity theories. So first, I will talk about acceleration bounds from cosmological equations. I will consider n scalar fields phi a. What I will say is not necessarily based on string theory. It's just scalar field cosmology. But of course, we are closely connected to string theory. For instance, we can find conic normalized scalars in string theory unless they're stabilized. Typically, we have a dilaton and some radions. We can also have complex structure moduli, string moduli, and other fields. And we'll consider a multi-exponential potential, so a sum of m terms of the form lambda I times the exponential of gamma IA times phi a, where a is contracted. So the couplings are encoded in this matrix gamma IA. Again, this has plenty of examples in string theory, for instance, curvature, fluxes, localized sources like branes, Casimir energy terms, they all take this form. They all give energies which take these forms. And but also this is used, for instance, in phenomenological constructions such as generalized assisted inflation, where the gamma IA matrix is diagonal. And then we consider the standard Friedman-Robertson-Walker metric, where we have a scale factor A, a Hubble parameter H defined as A dot over A, and the acceleration parameter epsilon defined as the time variation of the Hubble parameter, made dimensionless, so minus H dot over H squared. And we know that we have accelerated expansion if epsilon is smaller than 1. So with this field content, the cosmological equations have a quite complicated form. So we have the n scalar field equations with a double derivative of the fields, the double friction term, and a kind of force term. Then we have the first Friedman equation, which relates the square double parameter to the total energy. And then another Friedman equation that is actually not independent from the previous two equations, which relates the variation of H to the kinetic energy of the scalars. Now, it turns out that this system can be rearranged in an easier form if we make a convenient filter definition. So we can define some variables xa defined up to constants as phi dot a over h, and some other variables yi defined as the square root of the scalar potential terms divided by h. Then we can also rescale the Hubble parameter in terms of a function f, and the coupling matrix in terms of another matrix CIA. This is done just to get rid of the dependence on the dimension d. And it turns out that the equations that I wrote above take a much simpler form. So instead of the n field equations for the scalars, we have these n equations where we have x dot on the one end on the left-hand side, and on the right-hand side, we have a combination that only depends on the fields and doesn't have an explicit dependence on time. This is an example of an autonomous system of ordinary differential equations, and we use the properties of these kind of systems to constrain the late time solutions to the field equations. The other Friedman equations take an even simpler form. So the first Friedman equation becomes a topological condition on the xy plane. So the xy variable have to be on a sphere or a generalized hyperbola if some of the scalar potential terms are negative. And the time variation of the double parameter here expressed in terms of f is just proportional to minus x squared. So what we found is a generic bound. So here I reported an explanation just for the case where the scalar potential terms are all positive. But the bound is more general, as I will comment later. This is just for because it's slightly simpler to explain what the bound means. So the proof is in the paper. It requires some mathematical, it requires mathematical rigor. So I didn't. I'm not going to talk about this in this talk, but you can find the details in the paper. So the essential idea is that we have to define some constants, gamma infinity a, in the following way. So we define this constant to be gamma a as the minimum of the couplings gamma ia for each field a, where we scan over all the scalar potential terms if these are positive. And instead, if they are non-positive, we define this gamma infinity a to be 0. And then we find these analytically time bounds. Analytic because we have a proof that this is always the case without essentially an assumption. So epsilon is bounded from above by d-1, so it's something that just depends on the number of dimensions. And from below by this quantity, d-2 over 4 times gamma infinity squared. And this is a very strong bound, and it's not too hard to visualize it. So for instance, here, for two scalar fields with 3 scalar potential terms, we can define, we can check on a plane what this bound means. So essentially, given the matrix gamma ia, each row defines a vector, which we call mu. And essentially, in each direction, you have to take the smallest component of this mu among these mu vectors. And so, for instance, here for the field phi1, the smallest component is given by mu2. On the second direction, it's given by mu1. So we have we can define a vector which is essentially going on the diagonal of this rectangle, and the square length of this vector is what bounds the late time acceleration parameter. So the idea is that from the structure of the autonomous system, we find essentially these two considerations. So we always have, as I said, epsilon smaller or equal than d-1. And then we have to define an integral, which I call delta. This is the integral from the initial time to infinity of d-1 minus epsilon times h. We don't have a deeper understanding of this integral, but the value of this integral is enough for us to constrain the late time epsilon. So if the coupling gamma A is small enough, where we can quantify what this means exactly, and if this integral is infinite, then at late times phi dot over h is bounded from below by this quantity gamma A. Then from the from the Friedman equations, we know that the time variation of h is dictated by the kinetic energy, so we have to square this quantity. And in particular, because this quantity is bounded from below, we get the bound, the dimension. Epsilon has to be larger than d-2 over 4 times gamma infinity squared, where here we are excluding the non-positive gammas because the inequality can only be squared if we are sure that all terms are positive, that both sides of the equation of the inequality are positive. If instead the integral is finite, we actually can constrain epsilon exactly at late times and show that that is d-1. And in particular, this is always true if this quantity that we define gamma infinity squared is larger than 4 times d-1 over d-2. The intuition of this is obviously that when the potential is very steep, we cannot have acceleration. We can actually do a little bit more. So as I presented it, the bound is basis dependent, but actually we know that the system has a rotational invariance. We can rotate the basis of in-field space, which corresponds to the inverse rotation in the parameter space. So here I gave an example. For instance, here we have that the smallest coupling in the direction of the first field is negative. So the gamma infinity will receive contribution just from the second direction. So it would be, so epsilon would be bounded from below at late times by something proportional to this vector. But actually with a field rotation, we can maximize the lowest value of the bound. And again, this is very simple geometrically to visualize. So up to here, there is nothing that is intrinsically string theoretic. This is just a late time bound that always applies to multi-field, multi-exponential potentials. In string theory, we can do a little bit more because we find an obstruction to acceleration due to the dilaton. So the idea is that you can consider a string theoretic potential in general. So these are a potential that is generated perturbatively. So we didn't make any specific assumption, except that this could be the square of some R forms. It could have some contributions from the radion, from the string frame radion, if there is a compactification involved. So this is parameterized here as the exponential of minus kappa sigma, where sigma is the string frame radion and kappa is just a number. Crucially, this also features the exponential of minus chi e phi, where phi is the 10-dimensional dilaton and chi e is the Euler character of the worldsheet topology that weighs the string perturbative order at which this potential is generated. Now, if you dimensionally reduce this potential to the dimensional Einstein frame, in general, you find something like this. So it is the exponential of the d-dimensional dilaton, canonically normalized, and of the string frame radion, canonically normalized too. So for the string frame radion, we find a model-dependent coupling, which we can write, but I didn't report it here because it's not so informative, at least for what I want to say, because it depends on R and K. And instead, for the dilaton, we find a universal structure. So this coupling depends only on the number of dimensions and on this other character. And well, we know that in string theory, chi e is bounded from above by 2, which corresponds to 3-level couplings. And this immediately translates into a lower coupling for a lower bound for the coupling of the d-dimensional dilaton. This has to be larger than or equal to d over 2 over square root of d-2. And interestingly enough, this immediately rules out acceleration. Because you see that the gamma infinity squared is obviously larger or equal than this parameter, and this is exactly as to saturate the inequality epsilon larger than or equal to 1. Of course, we're not saying that string theory is always incompatible with acceleration. There are ways out to this obstruction. The theory could be at strong coupling, and in that case, everything that we said should be reconsidered, so it has no meaning. The dilaton could be stabilized, and in that case, we would have these model-dependent couplings, for instance, for the radiance. So in principle, one could still find acceleration, or there could be negative definite terms in the potential. In which case, the bound takes a slightly different form, which makes it less obvious to rule out acceleration, even though it's still pretty restrictive. So in the paper, we also considered what happens with negative definite scalar potential terms. So I wrote here for completeness how to define these gamma infinity A coefficients in this case. It's slightly more complicated because you have to consider the minima and the maxima of the couplings in the negative and the positive definite terms. But in the end, the bound still takes the same form. It's just that these gamma infinity squared couplings have to be defined slightly differently. But the bound that we showed is still essentially the same. So there are a few observations to make that we can make. So if only two terms appear in the potential, even if they are of opposite sign, essentially the bound has the same structure that as for positive potentials. So in particular, if there is a d-dimensional dilaton among the rolling scalars, then you still cannot have acceleration. Then we also observe a few qualitative tendencies. So many scalar potential terms tend to ease the bound. Physically, this is because it's easier to find shallow directions. And mathematically, it's because it's more likely to have a gamma infinity A coupling that has to be defined as 0. Another tendency is that instead many scalar fields tend to worsen the bound. And this is because the potential is steeper physically. And mathematically, you can see that because the gamma infinity squared term is additive. And finally, another consideration that is important is that here there is no slow roll involved. We never simplified the field equations with a slow roll kind of approximation. And actually, we have seen that unless gamma infinity squared is very small, at late time, we actually showed that there cannot even be slow roll. Okay. Now I will focus on instead a more specific solution to the field equations, which goes by the name of a scaling cosmology. Scaling cosmologies are solutions to the field equations where epsilon is constant and positive. So this corresponds to a power law scale factor, which means that A grows like T to a positive with a positive power, and this power is 1 over epsilon. Mathematically, these cosmologies correspond to critical points of the autonomous system that I defined before. And these solutions have been characterized analytically a while ago in the literature when the rank of the gamma I A matrix is M. Essentially, one has to define this matrix big M ij, which is essentially gamma times the transpose of gamma, where gamma is the coupling matrix. And one can characterize exactly the field space trajectory and acceleration parameter. So the fields grow with the log of t, and the acceleration parameter has this complicated expression. So it goes like the inverse of the sum of all the elements of the inverse matrix. And I will comment on this later. Again, two important considerations. Again, there is no slow roll, and one can check easily that for these solutions, the kinetic energy and the potential energy have the same parametric dependence on time. So in particular, the W parameter is not that close to -1 in general. And also in the slow approximation, one drops the second order derivative of the fields, but in this case, this is not correct because the second order derivative scales with time exactly in the same way as the double friction term. And then another important thing to notice is that contrary to what could be maybe the intuition, all scalar potential terms decay identically here. So all M terms fall over time like t squared. So there is no notion of dominating term in this kind of solutions. What is the relevance of these cosmologies? Well, first, we have seen that the late time scale factor is bounded from above and from below by power law behaviors, because I argued that epsilon is bounded by constant values independently of time, and that corresponds to two scaling solutions. Second, scaling solutions have been shown to be, in some cases, perturbative late time attractors. And the new result that will appear in our paper in May is that we can actually prove under certain conditions that scaling cosmologies are the late time attractors irrespective of the initial conditions. So it doesn't matter where the initial condition is, even if even if you start far from the solution, eventually over time the solution will converge to a scaling cosmology. So this happens, at least we proved that this happens when all the potential terms are positive definite, and then when these slightly more technical conditions apply. But this is not so important to follow the rest of the talk. So for now, I will just comment on some implications of the fact that scaling cosmologies are late time attractors. So essentially, I will characterize some properties of scaling cosmologies, knowing that in some cases they are the inevitable solutions at late times. So the first consideration to make is that, well, the field space trajectory is a line in field space. So you can define a vector normalized to 1 that follows this trajectory. And so first we can rotate the field space basis and find that we can describe the evolution with just a scalar, which I called here phi tilde. So geometrically, this is very simple. And but one important thing to stress is that even though the evolution is described by just one scalar, essentially all scalar potential terms contribute to defining what the scalar is. And the reason is what I said before. So all terms scale like 1 over t squared. So all terms are important in defining what this direction phi tilde is. And another important thing that we can observe is that we can define a scalar potential directional derivative. So essentially we contract the gradient of the potential with this unit vector. And we find that this is exactly related to the acceleration parameter. So, okay, I wrote this formula again here. So this directional derivative is exactly 2 square root of epsilon over square root of d minus 2. And of course, this is a very important result because it gives it relates clearly to the swampland de Sitter conjectures that appeared in the literature and that we've all been looking at. Again, a few considerations. There is no slow roll involved here. In general, the Sitter coefficient gamma, so the norm of the gradient of the potential, is actually always an overestimation of epsilon in these cases by basic vector identities. And more generally, we can also observe that this directional derivative and the de Sitter coefficient are actually unrelated to epsilon for non-scaling solutions, or at least not clearly related to epsilon for non.
Flavio, are you here? I think you're muted.
Okay.
Okay. You can go.
Okay. Yeah. So I was saying that epsilon is generally I was saying that the directional derivatives are not necessarily related to epsilon. And for instance, for a generic solution to the field equations phi bar, you can define a directional derivative where the direction in this case is not necessarily a straight line. So we define it just as the locally through the velocity of the field. And in this case, you can see that this directional derivative is not just proportional to square root of epsilon, but it has a correction factor, which depends on essentially the derivative of epsilon over time. So unless eta is 0, considering the directional derivative is not necessarily so useful. Okay, then before concluding, there are a couple of observations to make. Based on what I said, that is all scalar potential terms fall like 1 over t squared, you can select one of the terms labeled by some index I0 and do a field rotation and identify a scalar field tau tilde, which describes such that this potential is just the exponential of minus this field tau tilde. And by what I said, this field has to decay like 2 over, has to evolve over time like 2 over gamma tilde times the log of t, because where gamma tilde is the coupling that would appear in the potential, because this term, the I0 has to fall over time like 1 over t squared. Now, a simple application of this is the following. You can use this field tau tilde to measure time. So first of all, this gives you a way to express the Hubble scale in terms of as an exponential of this field tau tilde. Then second, one can define the Hubble scale for the Kaluza-Klein scale for isotropic compactification. And this is a very simple expression in terms of the dilaton and of the radion. And if among the scalar potential terms, there is a term generated by a non-trivial curvature, we can use that non-trivial curvature to define tau tilde, so to measure time. And essentially, because all potential terms scale like 1 over t squared, this relates in a very specific way the Hubble scale and the Kaluza-Klein scale. And in particular, you can check that in these cases, there is no parametric scale separation. So essentially, this means that both the Hubble scale and the Kaluza-Klein scale have the same time dependence, and so 1 over t. And so in these cases, unless you have some parametrically large or some very large or some very small curvature, typically, unless you have very large or very small curvature, you cannot have a separation of scale, and so the compactification ansatz is not justified. So these are very important results. Finally, we can comment on the convex hull formulation of the de Sitter conjecture. So if you have a set of n scalar fields and also n scalar potential terms, so the same number of fields and scalar potential terms, then you can define the convex hull of the couplings, and this is a n-1 dimensional plane. This belongs to an n-1 dimensional plane. So if you take the orthogonal line to the hyperplane containing the convex hull that passes through the origin, if this line also intersects the convex hull, we are able to show that the bound that I described initially is actually saturated, which means the acceleration parameter is exactly given by this parameter gamma infinity squared. This corresponds to the distance of the convex hull from the origin. And moreover, this also explains this formula for epsilon that I mentioned. And this distance, if you check how to define the convex hull, this is exactly that complicated formula for epsilon. So this is a proof of the conjecture in the paper, in a paper that appeared last September, even though there it was argued with the incorrect assumption of slow roll. But as we have seen, there is no slow roll here in general. Conclusions. unless I'm short on time. I don't know. Okay, so we have seen an analytic bound for the late time acceleration parameter. We have seen possible tension for acceleration, and even more, and even an even stronger tension for slow roll. Then we have commented on a string-theoretic obstruction to acceleration due to the dilaton. This tension, however, can be relaxed if there are negative definite terms in the potential, or if the dilaton is stabilized. Then, concerning scaling cosmologies more in detail, we've seen that they are very closely tied to the late time behavior. We have proved that for positive only scale potential terms, they can be late time attractors, and we actually quantify exactly when we are sure that this is the case. We have seen the inappropriateness of the slower approximation, and we have related a directional derivative to acceleration in these cases. Then a final slide to comment on the relation of this with the swampland program. We've seen some universal analytic tests of the swampland of some of the swampland conjectures. We have a generic bound for cosmic acceleration at late times, and in particular, as I already mentioned in the previous slide, we have a in particular string theoretic obstruction due to the dilaton. Then for scaling cosmologies in particular, we have seen an exact relationship between acceleration and the scalar potential derivatives. And then as to applications, we have seen that there cannot be scale separation if there is a non-trivial internal curvature. And we have seen analytic proof of the convex hull formulation of the de Sitter conjecture under assumptions that we quantified. Finally, things that we want to emphasize: the tadpole conjecture claims that it's hard to stabilize all the complex structural moduli in a string theory compactification. And a simple observation that you can make is that this could probably provide another obstruction to acceleration, because as we have seen, many scalar potential terms tend to go against acceleration. And finally, I would like to end emphasizing the importance of dynamical considerations in the swampland program, because as we've seen, we can learn a lot, not just by the structure of the potential, but actually by solving the equations. Okay, thank you.
Thanks a lot, Flavio. Do we have questions? Okay, Jose, go ahead.
Hello, can you hear me?
Yeah.
Okay, thanks for the talk. I wanted to make a couple of questions, but first of all, I would like to clarify that we do not assume slow roll for the convex hull. Is that we don't assume it. We at the beginning of the paper, we use it to introduce the gradient flows. But if you check the equations, we use equations that do not assume slow roll. And I wanted to ask about the scaling cosmologies. Can you come back to this plot of the direction? Okay, if I correctly, yeah, okay, then this vector is constant, right? It cannot vary.
Yeah.
Okay, so then you have a geodesic in the field space. But then I wanted to point out that when you say that the epsilon is not the gamma, actually for geodesics, the term that you said, the derivative, vanishes. So actually they are the same for geodesics, which is the case for all scaling cosmologies. If you define it.
Yeah, so yeah, actually I have a backup slide about this. So yeah, so these are a special feature of scaling cosmologies. So because the second derivative has the same time dependence as the Hubble friction term, you can see that on shell because this you find that the relationship between the scalar the first derivatives and the gradient of the potential, and because the trajectories align, this term is constant, and so it happens by accident that for scaling cosmologies, the late time solution is also following the gradient flow. But this is, as far as I see, just a coincidence, because you have something similar with slow roll, but with a very different assumption, which is that you can drop the second derivative term. And so even though the trajectory is the same, the time dependence of the solutions will be different. So they will describe very different.
Yeah, actually, I find very nice because it's something that we were doing in the paper is to first assume the gradient flow and then check that it's a geodesic. So if it will be possible to take a general sum of exponentials and to show that the lifetime cosmology is always one of these scalings, then that will finish because I mean, like finding non-geodesics in cosmology is also interesting. They have interesting
but in this paper, in the paper, or with more details in the paper that we'll post very soon, we actually, I mean, we don't make assumptions. We prove that under if essentially the couplings are suitable, then you necessarily have the scaling cosmology. So we're not making any answers. We're just showing that is the analytic late time behavior of any solution.
Yes, that I agree. And finally, if I can make another question, maybe there are other questions. Yeah. No, then let's discuss it later. It's not quick, so let's.
Yeah. Okay. So maybe we can go on after. Are there any questions?
I have a related question. So for the scaling cosmology, at one point you show like a bound, I think, on. But I was a bit confused because so you I mean like you show this bound that you relate to the de Sitter conjecture. Where this gamma star is depending on, I mean, it is proportional to square root of epsilon.
Yeah.
But okay. So it means basically that you don't follow a geodesic, right? Because so you have like that.
No, so I would say that no. So we follow this line, which, as I've just discussed with Jose, happens to be the direction of the gradient. But what is interesting is that so essentially because this is a line, you can actually rotate the field space basis and see that you get the very natural intuition that if the potential is very steep, which means gamma is large, then you cannot have acceleration. And so essentially, if the coupling is very large, epsilon is large, so there is no acceleration.
The thing I'm confused about is that usually when you have like a geodesic trajectory, let's say that your square root of epsilon v, so basically what you have there, what you define as gamma, should be equal to epsilon. But here you have like that is bigger than square root of epsilon. So
but that is a different epsilon. That epsilon is based on the slow roll assumption, and so you would find something that is kind of similar to this equation. So this is a directional derivative, but you can also find you can see something similar for the gradient of the potential. So for this quantity,
you're saying that
if there is slow roll, this quantity is related to epsilon, to the time variation of the Hubble parameter. But without slow roll, this quantity is not related to epsilon so easily. There are correction factors like this one going like the first derivative of epsilon. But for the gradient of the potential, you actually find the corrections with the second derivative.
Okay, I see what you mean now. Okay,
it's more complicated.
Okay, I see. Thank you.
Okay, maybe we can stop here the official part. Thanks again to Flavio and Simon